All right, last class, we learned about sandwiches. What kind of sandwiches? Does anyone remember? BLTs. We learned about BLTs, and we were talking about BLTs because they're a helpful analogy for recipes. So let's go back and look at our wonderful BLTs that I spent too much time making. Right, so we've got BLTs, and we know how many of each ingredient is going to go into our BLTs because we've got a recipe, and our recipe functions like a chemical equation. So we know how much of each ingredient goes in. So for example, if I go into my fridge and it looks like I've got 12 strips of bacon, 4 strips for one sandwich, I could make 3 sandwiches. This assumes that I have bread, lettuce, tomato, and thyme to make the BLT, and assuming no sauces or anything like that. We extrapolated this. We took this to chemistry, and what we call this in chemistry is stoichiometry. So stoichiometry is just looking at the ratio of our ingredients. In our case, usually reactants to products or products to reactants. And we learned that we are typically going to be doing that in mass, and we left off on this one that I had given you some time to work on, and so we'll go through it pretty quickly here. I also wrote in the molar masses of each of the compounds up at the top, just in case that was a sticking point for you. So we wanted to know what mass of octane, so we're looking for the mass of octane, would be needed to generate 42.3 grams of water, and water is H2O. So we are going from grams of H2O to grams of octane, which is C8H18. In order to carry out this calculation, we need to first convert out of grams using molar mass to get to moles of our H2O, a common strategy. If we've got grams, we can convert it to moles. Sometimes you can go somewhere from there, sometimes you can't. In this case, we can. So we go to moles of H2O, and now we're in moles, and moles lets us use our stoichiometry, our ratio of our 2 things that we care about, the octane and the water. And that lets us figure out, because of our ratio between the water and the octane, how many of the octane we must have had to get a certain number of moles of H2O. We can go to moles, octane, and then at the end, we have to bring it back to grams of octane, C8H18. And that's also using molar mass. So stoichiometry, again, just a fancy word saying our ratio of the 2 things that we care about. In this case, it's 2 C8H18 to 18 H2O water. Any questions about our solution map? Again, this is a really common solution map. It's often grams to moles to grams. Okay, so starting with our 42.3 grams of H2O, we need to divide by our molar mass of our water, which is 18.015. This puts the grams on the bottom, the moles flip to the top, our grams cancel. And if we stopped here, we would end up with moles H2O, moles of water, which is right where we want to be with our solution map. Then we need to use our ratio of our balanced chemical equation. Since we have H2O, we want the 18H2O to go on the bottom, so the H2Os cancel out. Or we want the octane to go on the top so that we will end up with units of octane. Either way, we get there. And then the last step is to bring it back to grams, since grams is what we can typically measure. So we're going to use this 114.232 to do that. And now our moles from earlier cancels with the moles that we have in the denominator of our molar mass. The units that come through are grams and octane. And then we multiply everything that's on the top and divide by everything that's on the bottom. So 42.3 times 2 times 114 and change divided by 18, also divided by 18, the other 18. And we would be left with 29.8 after we round for 3 significant figures. So 29.8 grams of octane should generate 42.3 grams of water. Any questions about our process there? Any of the steps? All right. We can also do it from one reactant to multiple products. So we've got this reaction with ammonium nitrate. Ammonium nitrate decomposes to dinitrogen monoxide, di prefix meaning we've got 2 nitrogens, the mono meaning we've got 1 oxygen, and water, H2O. In a certain experiment, 45.7 grams of the ammonium nitrate, that's our starting material, is decomposed. It's broken down. Find the mass of each of the products formed. So we're starting with grams of ammonium nitrate, and we're going to mass of each of the products, the N2O and the H2O. So we're going to need some molar masses for this. Our general solution map, I'll write it up here at the top, is going to be grams ammonium nitrate to moles of the same chemical. And then we have to figure out how many of each of the products we're going to make. So we're doing grams to moles to grams, but for both of our products. And it saves us a step if we stop here and we split the calculation. So we can go to moles of our N2O to moles of our H2O, and we'll convert both of those to grams. Any questions about either of those? Okay. To save us a little bit of time, I'm going to just drop in these molar masses for us. Remember, if you've got questions, if you're not sure how to do stuff like calculating molar masses, Logan, our SI, has SI sessions Monday, Wednesday, 3:30 to 5:30. This would be a great place to go and review those, and I'm sure that he could come up with some new problems for you to practice or find stuff from our book online. Okay, so starting out our problem, 45.7 grams ammonium nitrate. We want to convert this into moles of ammonium nitrate. So we need to divide by our molar mass. So this will give us basically our number of dozens, our chemist's dozens, of ammonium nitrate molecules. And we know from our balanced chemical equation that 1 ammonium nitrate will degrade into 1 N2O and also 2 H2Os. And so we can use those ratios now because we've got basically the number of ammonium nitrates. So 45.7 divided by 80 and some change, 0.570 and some other stuff, moles of ammonium nitrate. And this is where it's helpful to split because we're going to be doing this, it would be the same first step for both of these products. And so we can just copy and paste the number and do it twice. So then for our ratios, the things that we care about, we've got N2O, we've also got H2O. So one of these will be going to H2O, one of these will be going to N2O. Let's do the top one, ammonium nitrate to N2O. For every ammonium nitrate that we decompose, how many N2Os do we produce? One, because there's no coefficient, so we just assume that it's a 1. So it's a 1-to-1 ratio. 1 N2O out for every 1 NH4NO3 that we put in. And then to get the grams of the N2O, we use our molar mass, the 28 and change. For our other product, our water, for every ammonium nitrate that we put in, we get out how many H2Os? 2. So are we multiplying by 2 or are we dividing by 2? Multiplying by 2 because we're going to 2H2O. And the NH4NO3 goes on the bottom. Then we multiply by our molar mass for water, and we'll get some amount of grams of H2O. Typically on exams, you won't be asked for 2 products. You would just be given 1 product to find. So this one rounds to 16 grams of N2O. And for water, it's 10.3 grams of H2O. All right, so we talked about, you may remember, with the sandwiches. I go to the fridge, I find out I've got 12 pieces of bacon, I can make 3 BLTs. Let's say I go to the pantry where I keep my bread. You know, I'm fancy, I have a pantry. And I have 8 slices of bread. I check the fridge, I've got 5 pieces of lettuce, 8 slices of tomato. How many BLTs can I actually make? Because one of the ingredients, I'm probably going to end up a little bit short. So like if I just lay out all my bread, all my everything, right? I'm probably going to run out with a couple sandwiches where I don't have quite enough bacon, I don't have quite enough bread, I don't have enough lettuce maybe or tomato, right? There's something that I'm going to be short on. And this also happens in chemistry. So let's say that we've got these amount of ingredients. How many BLTs can we make with each of these? So with our strips of bacon, 12 strips of bacon, it takes 4 strips for each sandwich. So 4 bacon in, 1 BLT out. So I could make 3 BLTs given the amount of bacon that I've got. Okay, so I can make at least 3 sandwiches with the bacon. But what about our lettuce? Well, it's 1 piece of lettuce to 1 BLT because we're not big fans of lettuce in this recipe. So 5 lettuce, it's a 1-to-1 ratio. So I could make 5 BLTs just based on the amount of lettuce that I have. Now let's think about this for a second. Can I actually make 5 BLTs? I cannot make 5 BLTs. Why not? I do not have enough bacon, right? So the maximum that I can make still is 3 BLTs. So let's see if any of our other ingredients run out before our bacon. So we've got 8 slices of tomato, and we've got 2 slices put in equals 1 sandwich coming out. So 1 BLT out for 2 slices of tomato in. I don't know why we would have pre-sliced tomato in our fridge, but maybe we did burgers last night. So I could make 4 BLTs. Again, though, I can't make 4 BLTs. I just have enough tomato to make 4 BLTs, but my bacon would still run out first. Still limited by my bacon. And then the last thing to check would be our bread. We can see that with 8 slices of bread, 2 slices of bread put in, it would be the same situation as our tomato. We would have 4 BLTs that we can make with our bread. So we've got enough bread, we've got enough lettuce, we've got enough tomato that we could make more BLTs, but again, our bacon is running out. We just don't have enough bacon. So if this was a chemical reaction and each of our ingredients were reactants, then our bacon is what we would call our limiting reactant. So our limiting reactant limits the amount we can make. Or another way of thinking of it is that it runs out first. So at most, we could make 3 BLTs because I simply don't have enough bacon. If I go to the store, or if I go ask my neighbor, I'm friendly with my neighbor, and they've got some extra bacon, I get a couple extra slices of bacon. If I get another 12 slices of bacon, our bacon is no longer going to be our limiting reactant. It would get pushed off to something else because we've got enough bacon for more sandwiches. The 3 BLTs that we could make, that's our theoretical yield. Our theoretical yield is the maximum amount we can make. And so this is going to be based on the limiting reactant, the one that runs out first. There's sometimes some confusion with theoretical yield, that theoretical yield being the maximum amount that we can make. Sometimes people will say, oh, it's 5, or I switched the recipe on the BLTs with the tomato, so it should be 4. They might say, oh, it's 5, or it's 8, or it's 4, but remember that we'll run out of bacon first, and so 3 is the most that we can make. We can't make any more than 3 BLTs. Okay, so let's say that we're working on our BLTs. We're putting our sandwiches together in the kitchen. We're busy working on our sandwiches, and our dog, because we have a dog in this analogy, comes and he's being naughty. He steals a BLT off the countertop. So dog comes along, steals one of our sandwiches. We no longer have 3 sandwiches. We only have 2 sandwiches. One of them was lost along the way, RIP, our BLT. So even though we had enough bacon for 3 BLTs, we finished with only 2 BLTs because we're not the kind of person that shares food with our dog. Because I'm not the kind of person that shares food with my dog. That's gross to me. So if this was a chemical reaction, the 2 BLTs would be the actual yield. The actual yield is the amount that comes out, or the amount that is made. So we had our theoretical yield of 3 BLTs. In theory, with all of our ingredients, we could make 3 BLTs. Something went wrong, i.e. our dog was naughty. So we only ended up with 2 BLTs instead of 3. Oftentimes, in chemistry, our dog comes and steals some of our chemicals, our dog just being forces of the universe or lost to spilling or incomplete reactions. And so we have to measure our actual yield. In this case, it was 2. And with our actual yield, we can also calculate our percent yield. Our percent yield, in this case, our percent yield is always calculated by this formula, our actual yield over our theoretical yield, or our calculated yield, how much we should have been able to make. And since it's a percent in the name, we multiply by 100%. So 2 BLTs out of 3 possible BLTs, we were shooting 67% from the kitchen, which is not particularly good, I think, for making sandwiches. But again, our dog got in the way of our success. Do we have any questions so far? Otherwise, other than why are we putting our food in reach of our dog? Trust. Trust is why. Okay, so when we're doing chemical reactions, our actual yield has to be determined experimentally. For us in lab, if we're doing something with a percent yield, that means that we have to do the experiment to figure out how much we can actually make. Just like, well, making sandwiches isn't a great analogy, but like if we were going out to the basketball courts and we were shooting hoops, all of us, if we were shooting, would have different percentages of how many shots we make. Mine would be really low, and the rest of you would probably be a little bit better or comparable to me. And in the lab, it's a similar situation, but reversed, hopefully. Hopefully I'm doing the best in lab. So we would all get different percent yields of our product, and that's just based on how well we do our reactions, how careful we are with measuring things, how little we spill, other things like that. But it does have to be determined experimentally, or in the case of an exam, because this is something that I like to test on an exam, it could just be given to you as a number. So if you're not given an actual yield, you can't calculate a percent yield. Our actual yield is almost always less than 100%. There are some cases also where it can end up more than 100%, but typically we expect it to be less than 100%. Typically this is because some of the product does not form. Our reaction doesn't go all the way. For example, some of it is left unreacted. It's also likely that some of our product is lost in the process of recovering it, because usually we're ending up with like a small white powder, and as we're transferring it over, some of it stays behind. We accidentally sneeze, some of it gets blown off the scale. Something happens where we lose some product somewhere. So those are some reasons that we might end up with less than 100% yield. Question?
Ideally, you want that percent to be close to 100%?
Ideally, we want it to be as close as possible to 100%. That means that our reaction proceeded mostly to completion, like most of it reacted. We were using good reactants. Sometimes you can have bad reactants. And it also means that we probably didn't spill very much. Ideally, we're not losing really any to spilling. It's mostly just our reaction doesn't occur. And in the context of like how this shows up in actual like literature in scientific papers, people will often publish like this was our actual yield, this was our theoretical yield, this was our percent yield, and that's so that you, in the event that you wanted to go and do that reaction, can do the reaction, follow their steps, follow their recipe basically, and see, okay, how did I do compared to the people that published this paper? And you should expect your number, your output, to be close to what theirs is. So our percent yield, our actual yield sort of stuff, this is sort of like if you've read a recipe book and it says this makes 4 dozen cookies, that 4 dozen cookies is so that you know what to expect. So if you're baking for 20 people, you can bake a half batch, 24 cookies, and hopefully it'll turn out right. And if it ends up only making 10 cookies, then you know that you either screwed something up or maybe it's just not a very good cookbook. So this is the expected yield version for chemistry. So a summary of some of these terms. We've got limiting reactant. Our limiting reactant is the one that runs out first. It's completely consumed, it runs out, it makes the least amount of product. Our theoretical yield is the amount that we can make based on the amount of limiting reactant. And this assumes that everything goes perfectly. And it never does, but we still assume that it will. And then we've got the actual yield, which is the amount that we made, or the amount that somebody made, the amount that came out of the reaction, including all of the spills, including all of the reaction that didn't go to completion. This cannot be calculated. It can only be found by doing the experiment. And then we can calculate percent yield, which again is important for letting other people know, hey, this is how much it makes, like if you're sharing a recipe. Any other questions about some of those terms? Cool. Then we will stop there.